Okay, so now we're going to talk about the relationship between the angular quantities that a rigid body has and the translational quantities of individual points on that body. So when a rigid body is rotating around a fixed point, the entire body has an angular position, an angular velocity, and an angular acceleration. That represents the whole body. But individual points on the body, let's say this point, and every individual point is moving in circular motion around the fixed point. And what we want to do is come up with a way to relate the angular quantities to these translational velocity and accelerations that we're used to. Okay, so like for example, if this body is rotating, let's say that it's rotating this way, so that's the angular velocity of the body, and let's say it's slowing down, so its angular acceleration would be this way. Okay, what can we say about the velocity and acceleration of that red point and that green point? Well, this red point, since the thing is rotating, you can see clockwise, is going to have a velocity like this. Because the angular acceleration is this way, it's going to have a tangential acceleration like this. The centripetal acceleration is always toward the center of the circle, so that's going to be like that. Okay. We haven't talked about how to calculate the magnitudes of those yet, but these will be the directions. For this green point, the velocity will be this way. So you can see that's different than the velocity of the red point. That's going to be true with all of these. The tangential acceleration is this way. And the centripetal acceleration is this way. So all we need to be able to do is calculate the magnitudes of those, and that combined with being able to figure out the directions like this will let us calculate what those vectors are. I'm going to express these mathematical relationships between the angular and translational quantities largely in terms of absolute values. I am going to use capital V to indicate the speed, so you could think of that as the absolute value of the velocity. You know, when I'm talking about the magnitude of the angular acceleration, it's going to be that. The magnitude of the angular velocity is going to be that. The magnitude of the tangential acceleration is going to be that. The magnitude of the centripetal acceleration is going to be that. So these are the magnitudes I'm going to use. The speed of a point on the body is equal to the positive value of the angular velocity, or the absolute value of the angular velocity, times r. And this r is always going to mean the same thing for all of these. This is the distance from the fixed point, or I'll call it the pin, to the point that we're looking at. The magnitude of the tangential acceleration is going to be the absolute value of the angular acceleration times r with that same meaning. And the centripetal acceleration, well, we know that that's equal to v squared over r from when we did circular motion. Notice that if you use this expression for v and plug it in here, you can express it another way too, and that is omega squared times r. I didn't use the absolute value on the omega because squaring it gives you the positive value anyways. So squaring has the effect of using the absolute value. And so if you're trying to calculate the centripetal acceleration, these two are equivalent. You can use whichever one works. Okay, so let's see how this works in an example. So let's say we have a board like this, and that's the fixed point or the pin, and this distance is 0.75 meters. This distance is 0.25 meters, so the whole thing is 1 meter long. And this is the point P where we're going to calculate the velocity and acceleration. And let's say that we're given that omega is -5 radians per second and alpha is +15 radians per second squared. And we want to calculate the velocity vector and the acceleration vector of the point P at this instant. Okay, so if you want to visualize the direction of rotation, negative for the angular velocity means that this thing is rotating this way. Positive for the angular acceleration means the angular acceleration is this way. And this point P is moving in a circular path around that fixed point, something like that. Okay, so I'm going to start out, this is in effect a circular motion problem, and I am going to first draw the circular motion of P. There's P. The center is that pin. Based on the fact that this is rotating clockwise, I'm going to draw the velocity vector this way. Based on the fact that the angular acceleration is counterclockwise, I'm going to draw my tangential acceleration this way. Centripetal is always toward the center. And now we'll start using the equations that you were just given. So V is equal to the absolute value of the angular velocity, so that's 5, times the distance from the pin to the point we care about, that's 0.75. And so V is equal to 3.75 meters per second. Well, from our drawing, we've already figured out that V is in the negative y direction. So I'm going to write this as the velocity vector is equal to negative 3.75 meters per second j. You know, the negative says it's in the negative j direction. Now we'll go to the tangential acceleration. This is equal to the absolute value of the angular acceleration times r. So that's 15 times 0.75. And so that is 11.25 meters per second squared. We see from our drawing that we've already figured out that it's in the positive j direction, positive y direction. So the tangential acceleration is equal to 11.25 meters per second squared in the positive j. And now the centripetal acceleration. We could use v squared over r with this 3.75, or we could use omega squared times r with 5. So I'll use that one. We got negative 5 squared times 0.75 gives us 18.75 meters per second squared. That's in the negative I direction. So the centripetal acceleration is negative 18.75 meters per second squared I. And then the total acceleration is just the sum of the centripetal and the tangential. So the total acceleration vector is negative 18.75 meters per second squared I plus 11.25 meters per second squared J.